Okay, so these are the most important functional groups you need to know and the conversions, and there might be a few more, meaning this diagram is not complete. And you guys have this diagram as a printout. So I did give this to you. I gave it to you in class. So if you sift through your notes somewhere in your actual file of your paper notes, this is in here, but it's also in the textbook. It's somewhere at the back of the textbook on page, I'll find it for you now, and I can at least write it down for you. It's in organic synthesis on page 460. So this is in page 460 on the textbook. So it is in your textbook on page 460, but you also have it as a printout. Now, when you look at this diagram, would you agree with me that there's a lot of information and it looks confusing?
Yes, sir.
Yeah, so it's not a nice looking diagram. There's a lot of messy stuff. So what we're going to do is we're basically going to learn them part by part. And then what you're going to do is you're going to take the little puzzle pieces and construct the table. So we're not going to try and learn the table off by heart. That's not what we're trying to do. What we're going to do is we're going to focus on individual conversions. So we'll focus on, for example, this over here, turning an alkane into a halogenoalkane. Cool. Then we'll focus on something like this, turning an aldehyde into a carboxylic acid. And what you'll see is that we'll do each one of these as individual topics, but what you've got to do is see the bigger picture at the end. And this is basically the bigger picture. Cool. Everyone happy with that?
Yes, sir.
Yeah.
Yes,
so the goal is not to learn this parrot fashion. The goal is not to learn this copy, paste, repeat. The goal is to understand all the components and be able to piece it together yourself. In other words, don't try to learn the diagram, learn the individual components and the connections between them. And then you basically sit with the blank page and you draw the diagram for yourself. That's basically what you're going to end up doing at the end. Cool. Good. Okay, so look carefully at the diagram on the previous page. Notice that there are no named molecules. I don't know if Angelica is here. Is Angelica here?
Yes, sir.
Good. So Angelica, I'm not picking on you. I remember something you mentioned in class. What you see on this diagram here are not molecules. None of these have named molecules. It's not ethane, methane, propane, propanol, methanol. These are just the functional groups. So they're not converting specific molecules into other specific molecules. It's one type of functional group into a different type of functional group. Cool. So there's no named molecules. You only see functional groups. So it's only functional groups. So when we modify or change a specific molecule, we have first identify the functional group, and then we say what kind of conversions can that functional group undergo. Cool. And we will learn each new process step by step individually, and then you will need to know the bigger picture when we are done. Cool. So that's that. That's the first page. Good. Okay, so this is a very nice example. This is not something you ever have to know. So this example is not in the textbook. It's not in the syllabus, but I thought it was a nice example that you could relate to make sense of the topic. Okay, so you've all probably heard of aspirin. What you probably haven't heard of is that its chemical name is acetyl salicylic acid. So aspirin is the sort of common name. Acetyl salicylic acid is the actual name or the chemical name. And it's usually used to treat pain or fever. Now, you guys have mostly seen this as Disprin, meaning you don't buy aspirin, you buy what's called a brand, and the brand contains the aspirin. So a common brand that contains aspirin is Disprin. Yeah. Okay, so aspirin, this does not occur naturally. It's man-made. In other words, it's a synthetic drug. Synthetic meaning we can't just find it in nature. You can't find a specific plant, take the plant, extract the chemical, and there's your aspirin. Aspirin is literally man-made. So we make it using chemical reactions. So it's a synthetic drug. We find it. But another commonly found thing, and this is going to get quite confusing, is that you can also find a thing called salicylic acid. But notice that salicylic acid is not the same as acetylsalicylic acid. Can you see that? They're not the same thing. Yeah, everyone see that? I'm going to assume that's a yes. Good. Okay, so you see that salicylic acid is not aspirin, but salicylic acid is also a commonly used chemical. Cool. And then we can say we can use salicylic acid to synthesize aspirin. In other words, we can take the salicylic acid that we can find and we can turn it into aspirin. And that's the whole point of what we're learning. Cool. So the first synthesis of aspirin was in 1899, where this man, Felix Hoffmann, took salicylic acid and he converted it into acetyl salicylic acid. So he found a common source of the one on the left. So this was common. Oopsie, that's not the pen. Let's get the pen. Undo, 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 undo. Right, in black. This was common at the time, but this was unknown. So what he took was, he took what was commonly found, the salicylic acid, and he converted it into aspirin. Ooh, and then the question you have to ask is how? So how did he know that he could take salicylic acid and convert it into aspirin? And that's the whole point of what we're doing now. So that's the whole point of our topic. So look carefully at the structure of salicylic acid on the left. So that's the one on the left over here. So focus on that one. And what we want to do is we want to identify the functional groups. So I'm not going to give you the answers. I know it was on the next page. If you saw it, good. If you didn't, then you're going to have to guess, or not guess, you're going to have to see them for yourself. So there's 3 functional groups that I want you to name. So what 3 functional groups can you see here? Ooh, anybody? Anybody?
Carboxylic acid.
Correct. So this over here is a carboxylic acid. Correct. So that's a carboxylic acid. And you identified it by its structure, the double bond O and the single bond OH. Cool. What other functional groups can you identify?
Alcohol.
Correct. That's an alcohol over there. Alcohol. And then the last one, it's in the syllabus. They say you must be able to identify it. So you don't need to know it as a functional group, but you need to be able to identify it.
Benzene ring.
Correct. So this over here is the benzene ring. Cool. Okay. Then on the right-hand side, we're going to do exactly the same thing. So on the right-hand side, have a look at what's on the right and tell me what functional groups do you see on the right-hand side.
Benzene ring.
Correct. Benzene ring is the same. That hasn't changed. So that's exactly the same as that. And then what else?
The acid stayed the same.
Correct. The acid stayed the same. So that's the carbo acid. And then the last one's not so obvious. The last one is a bit hidden. And it's your good friend from biology. Yes, yes?
Yeah, is that an ester bond?
It's an ester. That's an ester over there. Cool. So you notice that it looks similar to the carboxylic acid, but it has 2 things bonded on either end. So this here is the ester. Cool. Now, if you look at the left and if you look at the right, would you agree with me that only one of the functional groups changed?
Mm-hmm.
Cool. So just summarize it. One of you quickly say it. What have we converted into what?
An alcohol into an ester bond.
100%. We've turned an alcohol into an ester. So if we highlight that, let's do that in green. We've taken the alcohol and we've turned it into an ester, and everything else stays the same. I still have the same benzene ring and I still have the carboxylic acid group hanging around the back there. Cool. Everyone happy with that?
So what happened? Was it oxidized, or how did the alcohol go?
You'll see later. So this is precisely what we're going to do. We're going to learn the functional group conversions. We're going to learn how to convert an alcohol into an ester, and we're going to learn the conditions, and we're going to learn what chemicals we can and what chemicals we can't use. Cool. So we will learn that. So if you go back to the original diagram here, this particular conversion is not on the diagram. Cool. So this particular conversion here is not on the diagram. So you can see there's a conversion between ester and alcohol. However, what I am telling you is that the conversion can go the opposite direction as well. You can go from alcohol to ester, and it's linked to the carboxylic acid. You'll see that later. It's linked to this over here. Cool. So you'll see later how we form esters using carboxylic acids and alcohols. Good. Everybody with me? Any questions so far? Cool. Any questions? No, we good? Good. Okay, let me just erase that. Sorry, if I don't erase it and if I save it, it's going to stay behind on the PDF. Okay, so look carefully at the salicylic acid on the left. The answers are in the notes. You see the benzene ring, you see the carboxylic acid, and you see the alcohol. And then there's a sentence that I just typed out here, and it says that chemists or the people who conduct chemical research know the functional groups have predictable patterns of reactivity. Chemists know that when a certain chemical is added, known as a reagent, to the salicylic acid, only the alcohol group will be modified. Cool. And then if you look at the structure of the salicylic acid, the acetyl salicylic acid, which is the aspirin, you'll see that everything is the same except we've created the ester. So the summary at the bottom here is what Angelica said. The summary is that we have converted an alcohol into an ester. Cool, everyone happy so far?
Yes.
Good, good, good. Good. Erase. And there we go. Okay, so it's very important, and this is it's not so much part of the textbook and the syllabus and the what you need to know to pass the exams and stuff, but it's important to think about what this means. Strictly speaking, salicylic acid, the starting thing, is not an ingredient of aspirin. It's a chemical used to synthesize the aspirin. So it's a chemical used to synthesize the aspirin. In other words, we take all of this on the left and we turn it into what's on the right. So in other words, when we're done with the reaction, none of this is left and we only have that. So we don't consider it an ingredient. We don't say that they exist simultaneously. The one gets converted into the other. Cool. So another example, just to sort of highlight the fact, is that if you take hydrochloric acid and you mix it with sodium hydroxide, you'll produce sodium chloride. But would you agree with me that hydrochloric acid is not an ingredient of NaCl? Would you agree with me?
Yeah. Yes.
Yeah.
So what do you mean by ingredient?
Yeah, so it's a very good question. Thank you. I'm glad you asked it because we need to explain it. So imagine that I gave you a little pile of salt. So on the left, on the right here, this is a small pile of salt and it's NaCl. And you have no idea where it came from. You have no idea how it was made. Would you agree with me that that pile of salt contains only salt, NaCl?
Yeah.
Yep.
Yeah.
So would you say that within that pile of salt, there's anything other than salt?
Yeah.
Yeah, nothing else, just salt. So would you say
Nothing
that
else, just
hydrochloric acid is an ingredient of the salt? In other words,
What do you mean by ingredient?
Exactly. So what I mean is if I found this in a packet, if I found a packet of salt and if I bought it as salt, and it was just NaCl, what's the only thing that the packet contains?
It's the salt itself, the NaCl.
The salt itself, correct. So very good question. What I mean by ingredient is, do I find HCl in that packet?
Oh, no.
No, and that's what I mean by ingredient. When I say ingredient, I mean, if I found aspirin on its own, I'm saying that it's just aspirin. Whatever I made it from is not there anymore. So whatever I made it from is no longer exists. Cool. And another way you can think about this is you can basically say, well, there's more than one way to make NaCl, and that's this equation at the bottom. So you know that a carbonate would react with an acid to produce sodium chloride. But would you agree with me that the two things on the left are not ingredients?
Mm.
And again, I'm being specific when I say I have a bag of NaCl. Does it matter how it was made?
No, it's only
No.
the products that
It's
matter.
there you go, 100%. Couldn't have said it better myself. It's only the products that matter. So we don't actually care about how it was made. What we're interested in is the product itself. And if you think back to IGCSE, we can just use basic stoichiometry. No, and this here, we can just use basic stoichiometry to say, well, if we get the quantities perfectly right, then all of the HCl and all of the NaOH will react, and the only thing I'll get left with is NaCl. In other words, there's no excess, there's nothing left behind.
Say that again, sir.
Ah, very good, good. So if I said, let's take 1 mole of the HCl, and if I took 1 mole of the NaOH, I would make exactly 1 mole of NaCl.
Okay, thank you.
Yeah. So what that's basically saying, whoopsie, that disappeared. Uh-oh. Don't know what I was busy with. I was busy with that. What it's saying is that in my container, once I've made NaCl, that's the only thing that exists, just the NaCl. So the chemicals that we use to make the NaCl are not ingredients in the NaCl. They are chemicals used to synthesize the NaCl. And that's the important stressing point over here that I can highlight for you. The important stressed point is this. So HCl is a chemical used to synthesize NaCl, but it's not an ingredient. If you need more clarity on that, just ask me again a couple of times. Think about it first and then ask me more times, and I'll explain it again if I can. Okay, so if you look at the contents of a packet of Disprin, this is literally if you looked on the box on the label. What you'll notice is that it tells you that in the container you find aspirin, which is the acetyl salicylic acid. Cool. The salicylic acid, or the beginning or the starting material, is not included. Yeah, it's not an ingredient in the formula. Cool, but it also contains other stuff. There's calcium chloride, maize starch, citric acid, talc, sodium lauryl sulfate, saccharin, that lime flavor, and all the other chemicals are just a mixture of added flavors, colorants, and stabilizers, meaning that in Disprin, the ingredients of Disprin are all those things. It's a mixture of the aspirin with a whole bunch of other nonsense added to it. But the only thing that cures the headache is the aspirin, obviously. Everything else is added just for flavoring and coloring and dissolving in water and whatever. But those are ingredients. Ingredients meaning they're all inside the Disprin tablet. So those are all contained within the Disprin tablet. They are not the chemicals used to make the tablet. They literally all exist as a mixture inside that tablet. So if I were to take that tablet, I could actually separate it. I could take the aspirin out, I could take the calcium carbonate out, I could take the talc out, I could take out the saccharin, I could take out the lime flavor, and I could isolate those specific compounds. All of those compounds exist within the tablet. But what is the one chemical that does not exist in the tablet?
The salicylic acid.
Correct. The thing that I used to make the aspirin, the thing that I used to make the aspirin. Yeah.
We're saying that the hydrochloric acid is not an ingredient, but are we also saying that the sodium hydroxide is an ingredient?
Exactly. I didn't specify, but yes, you're absolutely correct.
So both of them.
Neither of them are ingredients, correct, because both of them get used up in the process. So whatever we use up in the process to make something new is not an ingredient. What we call them reagents, or we use them chemicals that are used to synthesize something else.
Okay.
Cool. So when you look at the ingredients on aspirin, you'll see that there is aspirin. It contains aspirin, but it does not contain salicylic acid. It does not contain any of this original molecule, because how we made the aspirin is not important. The backstory of the aspirin is kind of like, okay, now we're done making the aspirin, forget about how we made it. Cool. So here's an interesting question. Do you think there's more than one way to make aspirin?
Yeah, probably.
Probably.
Probably, exactly. And that's the whole point.
Yeah.
It's that aspirin can be made using other chemicals as well. And if you look at this example here, with the two ways that we can make NaCl, there's probably hundreds of ways that we can make sodium chloride. But what we're only interested in is once we have the sodium chloride, we don't care how it was made. How it was made is irrelevant as long as we have the sodium chloride. Cool. Everyone happy with that?
Yep.
Good, good, good. So if it's a little bit confusing, don't stress. This is not really part of your syllabus and what you need to know, but it's how you need to think about synthesis. Is that once we convert something into something else, the starting material no longer exists. And then there's a very interesting controversial statement at the bottom, and it says, think about this when you hear people talking about the ingredients of vaccines. Yeah. So I'm not going to say whether I'm pro-vaccine or anti-vaccine. I'm just saying, think about the conversations you hear and think about what people say, and is what they're saying actually true? Ooh. So, yeah. Okay, so here's an interesting thing. Would you agree with me that highly concentrated HCl is dangerous? Would you agree with that? If I had highly concentrated hydrochloric acid, would you agree with me that that's not something you want to touch or play with?
Yes.
Yeah, you would agree with me on that. But if I gave you sodium chloride, and if I said, okay, eat the sodium chloride, would you eat it? Just basically table salt. I'm saying if I gave you table salt, if I said, here's table salt, would you eat the table salt?
Sure.
Yeah.
If it's on food.
Now, yeah, it's table salt. It's just NaCl. It's what you put on your chips and whatever. Okay. Now, if I told you that the salt that you just ate was made using hydrochloric acid, would you still eat the salt?
Oh no.
It's an interesting question. So if I used hydrochloric acid and it was absolutely 100% pure hydrochloric acid, no contaminants, and if the sodium hydroxide was absolutely pure, no contaminants, and I did it in 2 beakers that were absolutely clean with nothing that was dirty or nothing that could have killed you, would you drink that or eat that table salt or that NaCl?
Yes.
Yes, you would, because it's just sodium chloride. There's nothing else contained within that sodium chloride. The HCl no longer exists and the NaOH no longer exists. So would you agree with me that the HCl is irrelevant? Yeah, would you agree with me? Yeah, the HCl, it's dangerous on its own, absolutely, 100%. Concentrated HCl would kill you, but the minute you reacted with sodium hydroxide, it becomes NaCl, which is safe. Would you agree with that?
Yep.
Yep. And then I know it's a controversial statement, and I'm not going to tell you on which side of the debate that I fall, but if you think about the last statement and how people talk about vaccines, would you agree with me that when people often talk about an ingredient, they probably mean this chemical is used to make the vaccine?
Even though like the chemical becomes irrelevant afterwards.
Exactly, correct. So we might say, oh, they use formaldehyde to make vaccines. And then you go and Google formaldehyde and they say drinking formaldehyde will cause instantaneous death in small doses. And you're like, oh, formaldehyde is the most dangerous thing in the world. And you say, but it's in vaccines. What's the matter? Oh my goodness. And then you realize, no. Formaldehyde was used to make the vaccine, but the formaldehyde no longer exists. Cool. Does that make sense?
Makes sense, sir.
Yeah. So we can turn what we consider a dangerous chemical into something that we would consider as generally safe by converting it, by reacting it with something else and changing its properties completely. Cool. Any questions? Does anyone want to add anything? And we're not going to have a vaccine debate because it's overly controversial. But is there anything you want to add in terms of non-controversial topic?
Sir, this isn't completely related, but what's considered a drug?
Everything is considered a drug. Anything that acts on a chemical system to alter its behavior is considered a drug. So sugar is a drug. Sugar is a drug because it goes into your body and it reacts with a chemical pathway to alter whatever your body is doing. Alcohol is a drug, aspirin is a drug, cocaine is a drug, salt is a drug, everything is a drug.
Okay.
Cool. But in the context of organic chemistry and in the context of what we're going to learn, the drugs that we're going to learn about are all organic molecules, meaning they contain carbon, hydrogen, and oxygen.
Right. Wait,
So
carbon,
drugs are
hydrogen,
natural.
oxygen.
Okay, so here's an interesting thing. The salicylic acid on the left-hand side can be made using phenylalanine. So who's heard of phenylalanine before?
Mm-mm.
Phenylalanine. Some of you in biology must have heard of that. Think of amino acids.
I think it's at the back of the textbook.
Correct.
Is it
When they
an
list
amino
amino
acid?
acids.
It
I
is.
only know
It's
glycine.
correct. So
Yes.
it's an amino acid. So here's a very good point, and I'm glad you asked the question, is we can get phenylalanine naturally. So we can find this in nature. This is naturally occurring. Cool. We can turn it into salicylic acid, and we can take the salicylic acid and turn it into aspirin. So no, not all drugs are naturally occurring. In fact, most drugs that we take are synthetic. Most drugs that we take are man-made. So most drugs that we take are man-made.
Mm-hmm.
Which is controversial on its own, which is actually, I mean, if you go to the bottom statement, let's not go there because it's a whole can of worm. But yes, it's controversial because it is man-made, it's synthetic. We're putting something into our bodies that nature didn't make itself. So nature never intended us to have aspirin. We kind of cheated the system.
Yeah, but I mean, it's just like for the greater good, you know?
Yeah, for sure. But I mean, sugar occurs naturally, salt occurs naturally, vanilla essence occurs naturally, those you can extract. Aspirin is synthetic. We made it to help cure pain. So we did cheat the system a little bit. So I'm not going to tell you which side of the debate I fall on because it's a very controversial topic, but at least it gets you thinking about the topic. Cool, guys. I'm gonna end the meeting there. Take a long break. Take like a 10-minute break, and then come back at 1:45. Also at 1:45. Just for a quick, like a 10-minute lesson in about 10 minutes.
Yeah. So
Yeah.
what are we like applying this concept to? Very
good question. That's the next lesson. So I'll give you two basic examples. I'll give you two very simple examples that you'll understand. Cool?
Okay.
Cool. So in 10 minutes, take a break and then come back in 10 minutes.
And sorry, I wanted to also ask regarding the isomers, we did two, right? Two structural isomers. We did the chain
and we basically talked a little bit about, we talked briefly about positional in class before the lockdown.
Yeah, the positional one, yes.
Correct. I'm going to leave isomers until you get back to class because I want you to play with the modeling kits. So when you get back to class, we'll play with the modeling kits and we'll do isomers as a visual topic because I want you to be able to see the molecules when you do the topic.
Okay.
But you don't need to know isomers to do the rest of the work. So we'll do the functional group conversions because that you don't need the modeling kits for.
Okay, cool.
Cool. I'll see you in about 10 minutes.